Last time, we started talking about particle kinematics, and with particle kinematics in 1D or moving along a line, the acceleration is the time derivative of the velocity, and the velocity is the time derivative of the position. And so if you're going, no, ddt. If you're going in the direction from position to velocity to acceleration, all you're doing is taking the derivative. So knowing the functions is enough. Just taking derivatives. But if you're going in the direction from acceleration to velocity to position, the functions aren't enough. Excuse me. You also need to be able to solve for those constants of integration. You're integrating. So you also need values that let you calculate the constants of integration. Okay, so, for example, say that the velocity function, v of t, is equal to 3t squared. First, let's figure out what's the acceleration as a function of time. And then second, what's the position as a function of time. So the first one for part A, we're going in the direction from velocity to acceleration. So knowing that velocity function is enough, we're just going to take the derivative. For the second one, we're going in the direction from velocity to position. So we need something else. We also need to know that, like, for example, so given that, does it say? I don't know if I chose one. Given that at time equals 0, position is equal to 2 meters. Okay, so we'll see how this all works. Okay, part A. The acceleration is the time derivative of the velocity. So that's 6t. And that's the end of it. For the second one, The position is the integral of the velocity. And so if you integrate this velocity function, you get t cubed plus c. Okay. But that c is arbitrary, so that's not an answer yet. That doesn't give us a position function. So now what we need to do is use this extra information to calculate what that constant of integration is. Have you done this kind of stuff before in calculus? Yeah, okay. So to use that, this is called the boundary condition. So to use the boundary condition, when t is equal to 0, position is equal to 2. So we have 2 is equal to 0 cubed plus c. Solve for c, and you get that c is equal to 2. And so the position function is equal to t cubed plus 2. Any questions about that? Okay, so now part C. Is the object moving in a positive or negative direction? And then part D, is the object speeding up or slowing down? Okay, so take a second, think about this, think if you can make sense out of those questions, bounce ideas off the people next to you, and then I'll talk about it.
Well, we're saying no negative. Keeping up. No, no negative. No time. Yes.
No.
It's always speeding up. It doesn't go before.
Oh, yeah, okay. It doesn't go before.
Okay, so how do we know whether it's moving in the positive or negative direction? Which of these functions tells us the direction that it's moving? Actually, what we want to look at is the sign of the velocity function. So the sign of the velocity tells us the direction of motion. Velocity function was equal to 3t squared time can't be negative. V is always positive. So it's moving in the positive direction. Okay, what about speeding up and slowing down? Take a second and think about that and talk about that.
What? That's not right.
Okay, so what of these functions, what tells us whether an object's speeding up or slowing down? Combination of two things. Yeah, acceleration and velocity. If they have the same sign, it's speeding up. If they have opposite signs, it's slowing down. So if velocity and acceleration have the same sign, it's speeding up. If they have opposite signs, it's slowing down. We already know from part A that the velocity is positive everywhere at every instant. So now let's think about the acceleration function. So acceleration as a function of time was t cubed plus 2. Time can't be negative. So the acceleration is positive everywhere or at every instant. So velocity and acceleration are both positive, which means it's speeding up. Yep. Did I go the wrong way? Yes, thank you. 6t. Acceleration. Okay, thanks. Still works. Any questions about that reasoning? Well, because you can't have a negative time. And so if the function is 6t, that's positive no matter what t is, as long as t is positive. It's not, like sometimes that you could have a function where it's sometimes positive and sometimes negative. This is just a case where you can't choose any positive value of time that makes the acceleration negative. You know, like there's a lot of possible times, but let's choose 4. 1, 6, 10, 40 pi. Plug all those in as time, and you get positive accelerations for all of them. But it's definitely not true that an object can speed up and then slow down and whatever if you have a more complicated function than that. Actually, that's the next example I think I was going to do. Okay, so for the next example, let's say the position function is cosine of 2t. Where this angle is given in radians. So first calculate the velocity as a function of time. Then calculate the acceleration as a function of time. Then find an instant where the object's moving in the negative direction. And fourth, find an instant where the object's slowing down. Okay, do this one on the board.
Pretty close.
All right, so if the position is cosine of 2t, we're going in the direction we like, where we don't need to deal with the constants of integration. We're just taking derivatives. So the velocity function is the time derivative of the position, which is negative 2 sine of 2t. And then take another derivative to get the acceleration. And you get negative 4 cosine of 2t. So now, I mean, you could just, one way to do this is to just plug in a bunch of numbers into your calculator until you get an instant where the velocity is negative, and then another instant where velocity and acceleration have opposite signs. But I think the easiest way the best way to think about this is to plot out these functions. So the position versus time graph looks like this. That is cosine of 2t. So draw a cosine function. And then, so this is position, this is time. We know that for just a regular like cosine of x function, this point here is at pi over 2. You know, x is pi over 2. Well, our argument for our cosine function is 2 times something. So think of when 2t, what does t have to be for 2t to be equal to pi over 2? You know what I mean? Anybody with me?
Half of one usually.
Yeah, right. And so this has to be pi over 4. This has to be pi over 2. 3 pi over 4. And this is pi. You understand the reasoning on that? And then we can do a graph of the velocity versus time. That's a negative sine function, so it goes like this. And again, all of these points are half of what they would be if it was just a regular sine function. The amplitude is twice as big, but this would be pi over 4, pi over 2, 3 pi over 4, and pi. And then acceleration is a function of time. That's a negative cosine function. So that's going to go like that, where this point is pi over 4, pi over 2, 3 pi over 4, and pi. And now you're just looking for places where, so to figure out when it's moving in the negative direction, we just have to figure out when the velocity is negative. And it's negative, you can see all the way from time equals 0 to time equals pi over 2. Any questions about that? And then as far as when it's going to speed up, no, I think I said slow down, didn't I? Where's it slowing down? So we're looking for any place where the velocity and the acceleration have opposite signs. Okay, so let's just take it. We have what, 1, 2, 3, 4 intervals. Let's just look at each one of those 4 intervals and see what's going on. Compare, where's the velocity? I'll do it like this. So those are the 4 intervals. So in this first interval, velocity is negative, then negative, then positive, then positive. For acceleration, it's negative, then positive, then positive, then negative. So on the first interval, they're both negative, so it's speeding up. In the second interval, there's a negative and a positive, so it's slowing down. Third interval, positive, positive, so it's speeding up. Fourth interval, negative, positive, so it's slowing down. So from when time is between pi over 4 and pi over 2, it's slowing down. And when time is between 3 pi over 4 and pi. Any questions about that? Another way you can think about that is, well, there's 2 more ways I guess you can think about it. Something's speeding up if its velocity is getting farther from horizontal, right? Horizontal means that the thing has no speed. And so you can just look at the position versus time function and see when the slopes are getting steeper and when they're getting less steep. When the slopes are getting steeper, it's speeding up. When they're getting less steep, it's slowing down. So here, we're starting out at rest and then speeding up until there. Now here, it's steep, it's far from horizontal and getting closer to horizontal, so it's slowing down. Then speeding up again, then slowing down again. Any questions about that way of thinking about it? Or anybody just like, I don't care about that way? And then the last way to do it is pretty much the way that we did it in lab last week. So if you're looking at those slopes and thinking about, looking at those tangent lines and thinking about the signs of the slopes, that tells you the instantaneous velocity sign. And then if you think about whether it's concave up or concave down on the position versus time graph, that tells you whether the acceleration is positive or negative. So here, all of those slopes are negative. It's concave down, so acceleration is negative. So that has to be speeding up. from pi over 4 to pi over 2, all of those slopes are negative. It's concave up. So positive acceleration, so that has to be slowing down. On the next one, all the slopes are positive. It's concave up. So that's a positive velocity, positive acceleration. No. Concave. Yeah, that's right. So, so they're both positive, so it's speeding up. And then on the last one, all the slopes are positive. It's concave down. So it's a positive velocity, negative acceleration. So it has to be slowing down. Okay. So there's 3 ways to think about that question. So you can think of it as you have your choice of 3 ways to do it, or you can think of it as you have all these chances to square, to convince yourself that your answer is right. You know, you have a way to check yourself on this answer. Okay, one more. So this time, let's say the acceleration as a function of time is 1. And let's say that you're given a velocity that's equal to 0, time equals 0, and a position that's equal to 5 at time equals 1. So first, what's the velocity as a function of time? Second, what's the position as a function of time? Third, when is it moving in the positive direction? And fourth, when is it speeding up? Okay, back to the board. Okay, so we have that the acceleration function is equal to 1. The velocity is the integral of that acceleration function with respect to time. And so that's equal to t plus, I'll call it c1, some constant. And then the position function, there's the velocity. The position function is the integral of the velocity with respect to time. So that's equal to t squared over 2 plus c1t plus some other constant c2. And now we can use the boundary conditions. So boundary condition 1 says if you plug in 0 for time into the velocity function is 0. So 0 is equal to 0 plus C1. So C1 is equal to 0. And now we can, I don't care how, this might be more steps than you need to make sense out of this, but I'm going to update those functions now. So our velocity function now is equal to t, and our position function is equal to t squared over 2 plus c2. And now I'm going to use boundary condition 2 that says when time is equal to 1, position is equal to 5. So the position of 5 is equal to 1 squared over 2 plus c2. So c2 is equal to 4.5. And so the final functions are the velocity is equal to t, and the position is equal to t squared over 2 plus 4.5. Any questions about that? And then to figure out when it's moving in the positive direction, we're looking at the sign of the velocity function. It's always positive, so it's always moving in the positive direction. And then part D, when is it speeding up? Velocity is always positive, so we're looking for places where the acceleration is positive. A of t is always positive because it's just a constant 1. Velocity is always positive. So it's always speeding up. Any questions about any of that? Okay, so the most important types of kinematics problems, the ones that are going to come up the most common kinematics problems have constant acceleration. And the biggest reason that these are important is that, among other things, free fall and projectile motion have constant acceleration when the air resistance is negligible. In that case, the acceleration is equal to 9.81 meters per second squared down. No matter what the object is, no matter how fast it's going or whatever, the acceleration is 9.81 meters per second squared down. This constant is called lowercase g. And we're not going to do any problems where air resistance is not negligible. You know, everything, we're going to neglect air resistance on all of our calculations. So let's go through a derivation of a set of equations that represent constant acceleration, since that's going to come up so often. We already did it in that last example. You know, acceleration equal to 1 is a constant acceleration, but we're going to do it generally now. Given that the acceleration is a, and that's a constant, and that velocity is v sub 0 when time is equal to 0, and that the position is p sub 0 at time equals 0. Give expressions for the velocity as a function of time and the position as a function of time. Okay, so first I'll do the velocity. We know that the velocity is the integral of the acceleration. A is a constant, so that's AT plus C1. Our boundary condition says that when time is equal to 0, the velocity is equal to v sub 0. So v sub 0 is equal to a times 0 plus c1. So c1 is equal to v sub 0. And so the velocity function, v of t, is equal to at plus v0. And usually when you see it in textbooks and stuff, it's written in the other order. It's equal to v0 plus at, so I'm going to write it like that. That's the function for the velocity when you have constant acceleration. Okay, so will you go up to the boards and derive the position as a function of time? Okay, so the position function is the integral of the velocity function with respect to time. So that's the integral of the quantity v0 plus at with respect to time. So the position is equal to v0t plus 1/2 at squared plus c2. And then the boundary condition says that when time is equal to 0, the position is p sub 0. So p sub 0 is equal to v0 times 0 plus 1/2 a times 0 squared plus c2. And that tells you that c2 is equal to p sub 0. So the final function is v0t plus 1/2 at squared plus p0. And people usually write that in the order p sub 0 plus v sub 0 t plus 1/2 at squared. Okay, so one more thing to do. There's one more equation that we're going to use for constant acceleration a lot. So there's one more constant acceleration equation we'll use. And that is combine the velocity function and the position function by eliminating t from the equation. And that's going to give a relationship between position, velocity, and acceleration without time. I mean, all these things are still changing in time, but time isn't explicitly going to be in this equation. So see if you can figure out a way to do that. Okay. On the board. So what we're going to do is solve for time using the simpler of those two equations. So we have that v as a function of time is equal to v0 plus at. So we'll solve for time here. So time is equal to velocity as a function of time minus v0 over a. And then we'll plug that into the position function. So position as a function of time is equal to p0 plus v0 times the quantity v minus v0 over a plus 1/2 a times the quantity v minus v0 over a squared. And you end up with this sort of ugly looking relationship between positions and velocities and accelerations. And if you rearrange it, I'm not going to go through the algebra of it all, but you get this relationship that says 2 times the acceleration times the quantity position minus p0 is equal to the velocity squared minus v0 squared. So if you think of the time you're considering the time being considered as T sub F, and the position and velocity at T sub F as P sub F and V sub F. This is all just notation. We get the three constant acceleration equations. And they look like this. The first one says P sub F is equal to P0 plus V0 TF plus 1/2 A TF squared. These are all the formulas that we came up with before. I'm just writing T as T final, and P and V at T final is P final and V final. V final is equal to V0 plus A T final. And 2A times the quantity P final minus P0 is equal to V final squared minus V0 squared. Okay, so to use these, these are the 3, sometimes 4 steps. First, you have to choose instants corresponding to T0 and T final. So basically, you have to choose physical instants when you're starting and stopping your stopwatch. Second, eventually you'll probably stop doing this, but for now, at least mentally, you need to list the variables that you know and the variable that you're trying to solve for. And there's just a finite list of variables that you're considering. So you can go through them one by one. Do I know this? Do I know this? Do I want this? So these are time final, acceleration, P0, P final, V0, and V final. And then of those 3 constant acceleration equations, you're looking for one that has the variable you want, and every other variable in it is known. Every other variable in the equation is known. And then sometimes there isn't one equation that'll let you solve for the variable you want. So sometimes you need to find an intermediate variable, something you didn't know before. And then now that's a known variable and you can go back and do this process again. So sometimes you need to solve for an intermediate variable before you can find the one you want. Okay, so now I'm going to just do example problems for a little while. I mean, the rest of class today and probably on Tuesday a little too. There's one more bit of information about these that you should keep in mind when you use these equations. And that is in any constant acceleration equation. So notice at the instant an object changes directions, the velocity is equal to 0. Okay, so like an example of that is if you throw something up into the air, it slows down as it goes up, and there's an instant where the velocity is equal to 0 before it goes from going slowly up to starting to move down. Okay, so if you're ever looking for like the highest point in an object's flight, or the highest point that a ball rolls up a ramp, at that highest point the velocity is equal to 0. Okay, so let's say that a ball is thrown straight upwards with an initial speed of 10 meters per second. First, how high is the ball? Whoops. Let's say it's thrown from a height of 1 meter. So first, how high is the ball at its highest point? And second, how long does it take until the ball hits the ground? So how long is the ball in the air before it hits the ground? Okay, so for part A, so what's going on is there's the ground. Here's a point 1 meter off the ground. The ball's thrown into the air. At some point it turns around and comes back down. And we're trying to figure out how high it is at that highest point. So the steps, let's just go through these steps carefully. We have to choose. Oh, you know what? I'm sorry. Go back to these steps. I skipped two things that we need to choose. So we do have to choose those two instants. But we also have to choose, remember when I first talked about what you need to define before you can draw a position versus time graph or define position as a function of time. You have to choose these two instants, and you also have to choose a location that you call position equals 0. And you have to choose a direction that you're calling positive. So remember talking about that stuff, you have to choose where to set the ruler down, and you have to choose which direction to set the ruler. Okay, so the choices of your time equals 0 and your time final just have to do with where you know stuff and where you're trying to find stuff. You can only calculate values at time equals 0 and time final. So let's choose our time equals 0 to be when it's thrown. Our time final is going to be when it reaches the highest point. Our position equals 0. There are a couple of reasonable choices here. But let's choose position equals 0 to be on the ground. And then for free fall problems, we'll always choose our positive direction to be up. And now based on those choices, we can think about of these, how many variables was that? 7? 1, 2, 3, 4, 5, 6 total variables. We can think about which ones we know, which ones we want to find. There's some we don't care about at all. We don't know them, but we'd be happy never knowing them. So let's think about the variables that we know and what we're trying to find. And I'm just going to go through in this order. Okay. So we're going to think about, do we know or do we want the final time, the acceleration, initial position, final position, blah, blah, blah. So for part A, all we're trying to figure out is how high is the ball at the highest point. Do we know how long it takes for the ball to get to the highest point? No, but we're not looking for that, so I'm going to leave that off. Do we know the acceleration? Yes, it's in free fall. It's 9.81 meters per second squared down. We chose a positive direction up, so this is negative 9.81 meters per second squared. Do we know the position when time is equal to 0? Well, it says that it's thrown from 1 meter above the ground. Our 0 position is on the ground. Our positive direction is up. So what's the position when it's thrown?
1.
Positive 1, yep. That's meters. Do we know the final position?
0.
The final velocity is 0 because it's at the highest point.
Yeah.
but we're trying to find how high it is. This is the one that we're trying to solve for. Do we know the velocity when time is equal to 0? Yep. Yep. So the speed is 10 meters per second, and is it moving in the positive or negative direction? Positive. Yep. So v sub 0 is positive 10 meters per second. And do we know the final velocity? The velocity.
0.
Yep. When time is, when we're at t final, when we're at that highest point, it's about to turn around, so the velocity is equal to 0. So Vf is equal to 0. And now what we'd like ideally is one equation that has Pf in it, and everything else in it comes from this list of stuff we know. Because one equation, you can only solve for one variable. So of those 3 constant acceleration equations, are there any that work with this? It looks like this one will work. 2a times quantity Pf minus P0 is equal to Vf squared minus V0 squared. And you can keep all the units in. All the units will work out in the end. So 2 times negative 9.81 meters per second squared times the quantity Pf minus 1 meter is equal to 0 squared minus 10 meters per second squared. And so you get negative 19.62 meters per second squared times Pf plus 19.62. We have meters per second squared times meters, so this gives meters squared per second squared. Is equal to negative 100 meters squared per second squared. So negative 19.62 meters per second squared times Pf is equal to negative 119.62 meters squared per second squared. And can anyone have a calculator in front of you? Could someone divide that out for me? And then tell me.
Pf is 6.09.
6.09, I'll just leave it there. 6.09, and the units come out to be, when you divide meters squared per second squared by meters per second squared, you just get meters. And so the highest point is 6.1 meters, which is about 20 feet. Any questions about that process? Okay, so I think we can do part B. So now we're trying to figure out the total length of time that the ball is in the air. We're going to have to make new choices for the times because we don't care anymore about what's happening at the top of the flight. So time equals 0, we can still use when it's thrown. But now time final is when it hits the ground. Position equals 0. Let's still call that the ground, and the positive direction we'll always call up for free fall. Let's think about what we know and what we want. These are going to be different now because our time final is a different instant. You know, the position and velocity and stuff at that instant are going to be different than they were in part A. Do we know time final? Or do we want time final? We don't know it, but that's what T final is what we're looking for. Do we know acceleration? Yeah, it's still free fall, so acceleration is negative 9.81 meters per second squared. Do we know the position when time is equal to 0? Yep. Do we know the position when we're at time final? That was that was when our time final was when it reached the highest point, but now our time final is when it hits the ground. So 0 because it's on the ground. Yep. So P final is equal to 0. Do we know V0? That's positive 10 meters per second. And do we know V final? We don't. That's right. And it's an easy mistake to make to think, well, it hits the ground, the velocity is 0. Right? That reasoning sort of makes sense. But as soon as it hits the ground, we're not in constant acceleration anymore. The acceleration, you know, it's not free fall anymore. So these equations are only valid until the instant right before it hits the ground. And at that instant, it's still moving down at some speed we don't know. Okay. So don't make the mistake of thinking that when the object hits the ground, you set the velocity equal to 0. Setting the velocity equals 0 is specifying that you're at the highest point in the flight. Okay, so is there an equation that works with all of these? I think this one should work. PF is equal to P0 plus V0 TF plus 1/2 A TF squared. So 0 is equal to 1 meter. I'm going to leave the units out in this just to save time, but you could put all the units through and it would work out. Plus 10 TF plus 1/2 times negative 9.81 TF squared. So 0 is equal to 1 plus 10 TF minus 4.905 TF squared. How would you solve this for TF? That wouldn't work in this case. Quadratic formula is the easiest way, yeah. So very good. So TF is equal to negative 10 plus or minus square root of 10 squared minus 4 times negative 4.905 times 1 all square root divided by 2 times negative 4.905. Can someone tell me what those two are? Can you do that in your head? Yeah. Square root of. I want it to 4 significant digits. We're going to get a negative answer. Yes.
Something like
0.0955 or 0. Okay. And then there's going to be a positive answer.
is it non-responsive?
2.134. Okay. Hey, listen, shut up for a second. So we get these two answers. A negative answer and a positive answer. We're only looking for one time, so which one of these? We want the positive because we don't deal with negative times. What does that negative time mean, by the way? That's a rhetorical question. Here's what it means. If we plotted a position versus time graph of this motion, it would look like that. Yeah. This would be at 2.134. And if you continued that parabola into the non-existent, so basically if you imagine that this ball was in constant acceleration from before time equals 0, at 0.0955 seconds before time equals 0, that's when it would have crossed the ground. We specified, that we wanted to know the time when it was at the level of the ground. A parabola has 2 of those, but it doesn't have any physical meaning. The only one that has physical meaning is the one with the positive time. Okay? All right. See you tomorrow. Yeah, quiz tomorrow. It's on, there's 2 things. The quiz is going to ask questions about the notes, so you need to review your notes. And it's going to ask you to reproduce problems in the homework. I think that's right. Yeah. Let me look.
I didn't check the calendar.